Here we want to find the best predictor of y using a function of x called g of x. Now, best means we're going to minimize this expression here, the expected value of this squared difference. And then we will show that the g of x that minimizes this is the expected value of y given x. But before we start, I want to go through 4 notes or 4 results. Some of these are known, some of them might not be known, but we'll use them in the proof of this result. So the first one is if the expected value y is equal to the expected value of the conditional expectation of y given x. And so a quick proof of that is if we look at the expected value of this expected value, so this is a function of x, so you plug it in, integrate it, this, and times it's the f density, f of x, integrate over all possible f's or x's. This right here is the expected value of y times f of y given x, and you integrate it over y. Well, f of x and this can combine to just be f of xy. And then if we switch the order of integration of x and y, then we get this piece here. So the y is outside. We have f of xy dx. But when you integrate out x, you just get f of y. And then integrating y, f of y dy is just the expected value of y. So the next expression is expected value of y times a function of x given x. Is h of x, or that function of x, times expected value of y given x. And it sort of makes sense, because if you're given x, this is a constant, so you just take it outside the integral sign. And then a quick proof of that is we look at this expected value. By definition, it equals this, but that is a constant with respect to the y world, so you take it outside the integral. Well, this is just the expected value of y given x, and that's what we wanted to show. So result 3 is we have the expected value of y times a function of x. Okay, so by result 1, if we condition on it x and take the expected value, we just get what's here back. But by 2, this becomes a constant and can be moved out front. So by 2, we get the expected value of h of x times expected value of y given x. And this result will be used in our main result. And so here we have the expected value of y times expected value of y given x. Is equal to the expected value of this quantity squared. So the little proof of that is we're given this expression, then let's condition on it and take its expected value. So that's what we do here. And then so by 1, that's true. And then by 3, up here, expected value of y given a function of x. So here y times a function of x. Oh yeah, and then it's the so this piece actually can be taken out front, and then it's just the expected value of y given x of y, which is this. And then that's squared, so we get that. Okay, so the main result is this. We want to minimize this. So the way that our approach that we're going to use is we're going to add and subtract the same quantity inside this expression. So that's what we do here. Now we want to multiply this out, but we're going to keep these two together and keep these two terms together when we multiply. So you get this times itself, which is squared, this times itself, which is squared, and then 2 times that, which is this piece. We want to take the expected value of n in the expression. So we get the expected value of this plus the expected value of this plus 2 times the expected value of this. But let's look at this piece right here. And so what I want to do is multiply this out. So this times that, and then take expected value. So that times that, this times this, and then the expected value. Then this times that, which is this, and then that times that, which is this. Well, by 4 above, this is equal to the squared result. And by 3 above, this is equal to that. But we have this term minus the same term. And then we have this term minus the same term. So this drops out to 0. Okay, so thus, the only thing we have are these 2 terms. This term over here dropped out. So if we want to minimize this function with respect to g of x, so that means we're going to change this function around. You know, it'll become bigger and smaller, and we want to find the smallest possible. But if you look at this piece here, there's no g of x in it. So whatever we do changing this is a constant. So with respect to g of x, it actually doesn't play a part. This piece here is squared. So expected value of y given x minus g of x is this squared is always going to be positive. So we have a constant term times something that can be 0 or positive. So the way to minimize this function here is actually to minimize this. But the smallest it can go is 0. So if we can make this term 0, then we have minimized it. Well, if we set g of x equal to the expected value of y given x, then that's 0. And then we're done. So the expression is minimized when you set g of x equal to the expected value of y given x. Okay, so that's done. That's what we wanted to show. But one note is that this can, unless it's bivariate normal, it can be a pretty complicated nonlinear function. And we, you know, but sometimes we just want a linear function or a line to estimate y. And so we can find the best linear predictor of y. So let's let the expected value of y given x equal to this alpha plus beta x. So this is a line, and we want to find the an estimate of alpha and an estimator of beta. So to develop some notation, the mean of y is mu y, mean of x is mu x. The correlation by definition of this, but let's use the sigma xy divided by the standard deviation sigma x and sigma y. So as before, we want to minimize this expression. I'll call it y. First of all, I want to square there's the 3 terms here, and then bring in the expected value, and we get this. Okay. Well, then if we take the partial derivative of L with respect to alpha, then we get this expression. So here we get minus 2 expected value of y. Here we get 2 alpha, and then here we get 2 beta expected value of x. Set it to 0. And we do the same for beta. Set it to 0, and then solve this. And when you solve it, you end up with this expression. So alpha is mu x minus the rho, which is correlation, times standard deviation of y divided by the standard deviation x times the mean of x. Beta is just this. So plugging those into the equation and then simplifying a little bit, we get this. So this is the expression of the best fitting line. using X to fit Y. Okay, now let's go through a quick example here. So here we're going to let f of x equal 8 times xy over this region. And then you can integrate out y and find x, which is this. You can integrate out x and find y, which is this. And then the mean of each of those, mean and variances of each of those distributions you can find. We can also find the covariance of x and y using this expression here. F of y given x is this density divided by this density, and you come up with this. So the best predictor of y given x is this expression. Well, that's not exactly a line. So when we plug in what we did before, it can be shown that our line, the best fitting line, is this expression. Okay, so now to try to graph this, and I did it by hand, so take it with a grain of salt. So x goes from 0 to 1, and y went from, x to 1. So when we plot the line, you get that straight line right there. And then the best predictor of y given x is this, and that is the one that's a little bit curved there. So they both do a pretty good job of fitting the y. But there we go. Hope you enjoyed the video. If you like the video, please subscribe, and see you later.